Hi, so today I'm going to talk about Googology. Googology is the study of very, very large numbers. It derives from the word Google, which sounds very similar to the current search engine Google. And in fact, the search engine Google was named after an incorrect spelling of this original word, Google. A Google is a very large number. It was invented in the 20th century. I won't say who because that would be very uninteresting. It was invented by a 9-year-old child. That's a very amusing factoid, and its value is 10 to 100th power, or written out in decimal form, it will be similar to this, with 100 zeros behind the 1. I won't bother to write it out in full decimal expansion. That would take too much time. And that's exactly what Googology is all about. Numbers so large that it would take up nearly infinite time for you to write them down. And so, firstly, I'm going to explain a very well-known and used notation in Googology, the up-arrow notation, devised, often attributed to Donald Knuth. This is why it's called the Knuth Up-Arrow notation. And so the symbol of this notation introduces, not surprisingly, is the up arrow. And it's a triple argument function, an up arrow iterated k times. Iteration simply means repeating something. Those are the only 3 arguments in this function. So n single arrow m is equal to n to the m. So before I introduce this even further, let's get the concept of hyperoperations familiar with us. Firstly, the first hyperoperation is addition. N plus m. We call this the first hyperoperation because it's not the repetition of anything. What a hyperoperation is will be clear to you in a minute. Second operation is multiplication. Why is that? Because it's repeated addition. This is equal to n plus n plus n dot 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 plus n with m n's. And every hyperoperation beyond multiplication continues in this fashion. So n to the m is simply repeated multiplication. This is equal to n to the n times n times n times n dot 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 times n with m n's. Now, we already denote this with basic arithmetic symbols, so there would be no need to actually devise another notation to represent them. However, what's beyond exponentiation, or n to the m? That would be repeated exponentiation, represented by n double up arrow m, also called tetration. This is called tetration because it is 4th hyperoperation. Tetra is a Greek prefix. Sorry, I don't know what prefix it is. It's just a prefix for 4. And as you notice, there are 2 up arrows here. The number of up arrows represent what hyperoperation it is. There are 2 up arrows, meaning it is 4th hyperoperation. In general, with how many arrows it represents? With n arrows, it represents n plus 2 hyperoperation. So what is this equal to? This is equal to repeated exponentiation. N to the n to the n dot 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 to the n. How many n's are there? There are m n's. This is called a power tower or a power stack. And so in general, we can say n up arrow iterated k times of m is equal to n up arrow k minus 1 times of n up arrow k minus 1 times of n up arrow k minus 1 times dot 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 of n up arrow k minus 1 times of n dot dot dot. Let me write that out more clearly one more time. How many n's are there? There are m n's. And all this is equal to n up arrow k of m. So let's try this with an actual example, which we can actually quantify. 3 triple up arrow 3. This is called pentation, because it is the 5th hyperoperation. Pent is a prefix for 5. Maybe penta is the prefix for 5. I'm not sure. Anyway, this can be broken down into 3 tetrated to 3 tetrated to 3. What's 3 tetrated to 3? That'll be equal to 3. This expression is equal to 3 tetrated to 3 to the 3 to the 3, since tetration is repeated exponentiation, which would equal 3 tetrated to 3 to the 27th, because 3 to the 3 is 27th. This would equal 3 to the very, very large number, approximately 7.6 trillion. This would represent a power tower of height approximately 7.6 trillion. This is an insanely large number. In Googology, it's often called tree. But that's not very important. This number, if you had all the paper in the universe, and each number would fill up a Planck volume, the smallest possible volume for an object to fill up. This, you still couldn't write this number down because it is so large. Now, after this step, I believe it is appropriate for me to introduce a very large number using this notation. It is called Graham's number, developed by Ron Graham, a mathematician who was working in Ramsey theory. It's not important to know what Ramsey theory is, but he was solving a problem about higher dimensional cubes, and this number came up as the upper bound to the solution of this problem. The solution to this problem was either between 13 and this number, Graham's number. We denote it as G, or this lowercase g, subscript 64. Now, suppose there was this following function, using the Knuth Up-Arrow notation, defined by the following set of rules. 1. G0 equals 4. 2. Gn is equal to 3 up-arrow iterated Gn minus 1 times to the 3. So what would G1 equal? G1 would equal 3 hexated to, yes, that's what you call 4 up-arrows, 3. And this would be a very huge number because it would equal 3 pentated to that really, really large number. What is this really, really large number? It's the power tower of approximately 7.6 trillion height. So this would equal 3 tetrated to 3 tetrated to ... 3 tetrated to 3 ... 3. Sorry, ... With how many 3's? This many 3's. So G1 is a very large number. Are we anywhere close to Graham's number? No, as I mentioned before, Graham's number is G64. So let's imagine G2 first before getting to Graham's number. G2 is equal to 3 up-arrow iterated G1 times of 3. Each up-arrows gets us into a much, much bigger number. And G1 is a very, very large number. So what does that mean? That means G2 is very, very much larger, extremely larger than G1. And it grows even more for G3, which would equal 3 up-arrow iterated G2 times of 3. We repeat this until G64. G64 is what we call Graham's number, as I mentioned here. Graham's number is equal to G64, which is equal to 3 up-arrow G63 of 3. And we can represent Graham's number with a layer by layer. The first layer would be 3 up arrow, dot dot dot, up arrow 3, with how many up arrows? 3 up arrow, dot dot dot, up arrow 3, how many up arrows? 3 up arrow, dot dot dot, up arrow 3, and we can continue this for 64 layers until the very first layer, the lowest layer, is 3 hexaded 3, which is G1. So Graham's number is very, very, very large. But we can go even larger, and I'll tell you about that in next time's video. Thank you.